On November 7, 1940, in the state of Washington, United States, a modern bridge began to move in a completely unexpected way. The wind speed was approximately 19 meters per second, strong but not extraordinary. Yet that day, the Tacoma Narrows Bridge began to oscillate violently. At first, it moved up and down. Then the bridge deck started to twist. One side of the bridge rose while the other fell. In a short time, the structure began to twist in segments, as if the bridge were being wrung apart from both ends. Minutes later, the bridge collapsed. This event would become one of the most studied failures in the history of civil engineering. The Tacoma Narrows Bridge was a suspension bridge. A suspension bridge is a type of structure in which the bridge deck, the surface that carries traffic, is supported by vertical hangers connected to main suspension cables. These main cables transferred the weight of the deck and applied loads to towers and anchorages located at the ends of the bridge. This structural system allows suspension bridges to span very long distances, making them suitable for crossing wide bodies of water. The Tacoma Narrows Bridge was built to cross the Tacoma Narrows Strait in Puget Sound near the city of Tacoma, Washington. The bridge was completed and opened to traffic on July 1, 1940. At that time, it was the third longest suspension bridge in the world, with a main span of 853 meters. The bridge deck was approximately 11.9 meters wide and included 2 traffic lanes and sidewalks. Compared to its total length, the bridge was relatively narrow, giving it a slender and streamlined appearance. It was also the first suspension bridge of its type to use plate girders to support the roadway. Shortly after construction, engineers observed that the bridge began to sway and deform under windy conditions. These oscillations were noticeable along the length of the bridge. The movement was significant enough that engineers began conducting wind tunnel experiments to study the airflow characteristics around the bridge structure. These studies aimed to understand how wind interacted with the bridge, as the oscillations were evident even before the collapse. On November 7, 1940, just 4 months after opening, the oscillations intensified. The bridge began to undulate visibly. Soon after, the deck started to vibrate torsionally. This means that different parts of the bridge rotated in opposite directions. During this phase, the deck vibrated in segments with a frequency of approximately 36 cycles per minute. The motion then transitioned into a more severe torsional mode with a frequency of about 14 vibrations per minute. In this stage, the midpoint of the bridge remained nearly motionless while the two halves twisted in opposite directions. This motion generated high stresses throughout the structure. The hangers failed and the main span collapsed. As segments of the deck fell into the water, their weight pulled the towers inward, causing cracking and leading to the total collapse of the bridge. Despite the dramatic failure, no human lives were lost. While the deflection theory enabled lighter and more economical bridges, the Tacoma Narrows Bridge extended this concept too far. The bridge had very small resistance to twisting, making it highly flexible torsionally. In addition, the plate girders had a relatively flat H-shaped cross-section, which proved to be aerodynamically unstable. This shape allowed airflow to separate easily at the edges of the girders, generating vortices that matched the oscillation of the structure. The wind-generated vortices moved the girders, and that movement generated new vortices. This feedback process caused the oscillations to grow rapidly. The collapse was caused by self-excited oscillation induced by lateral wind. In this phenomenon, wind does not merely apply force to the structure. Instead, the motion of the structure itself generates additional aerodynamic forces that continue to feed the vibration. This mechanism allowed oscillations to build up quickly until the structure could no longer withstand the stresses. When the Tacoma Narrows Bridge was designed, this type of aerodynamic interaction in long-span suspension bridges was not yet fully understood. After the collapse, the Federal Works Agency appointed 3 engineers to investigate the failure: Theodore von Karman, a well-known hydrodynamics expert; Othmar B. Amann, consulting engineer for the George Washington Bridge; and Glenn B. Woodruff, consulting engineer for the Golden Gate Bridge. Their report concluded that the bridge had been well designed and built to safely resist all static forces, including wind loads typically considered in similar structures. However, the report also stated that it had not been realized that aerodynamic forces, previously known to be disastrous for lighter and shorter flexible bridges, would affect a structure of such magnitude. The investigators recommended further research and testing to develop methods for calculating aerodynamic forces acting on suspension bridges. The bridge was later redesigned and rebuilt using a different structural approach. The new design incorporated open trusses, stiffening struts, and openings in the roadway to allow wind to pass through the deck. These changes significantly reduced twisting and improved aerodynamic stability compared to the original bridge design. The collapse of the Tacoma Narrows Bridge marked a turning point in structural engineering. From that point forward, engineers recognized the need to consider self-excited oscillations in structural design. Wind tunnel testing and dynamic analysis became essential tools for understanding the behavior of flexible structures exposed to wind. These methods were incorporated into the design of long-span suspension bridges worldwide. The collapse of the Tacoma Narrows Bridge demonstrated that structural safety depends not only on strength and static load resistance. It also depends on understanding how structures dynamically interact with their environment. The investigations that followed the collapse clarified the mechanisms of vibration and emphasized the importance of rigid girders and aerodynamic stability. Although the Tacoma Narrows Bridge existed for a short time, its failure provided critical knowledge that permanently changed the design of suspension bridges and the practice of structural engineering.